First, I want to thank the committee for inviting me to speak today at the Engineering Expo. This annual event is great, and it's got quite a history. There's many great and successful engineering graduates that have come from KU over the years, so they had lots of great choices, and I consider it to be an honor to speak today at this year's Expo. So my talk today, as you can see, I've titled it, "Why Would I Want to Be an Engineer?" It's a lofty question, but hopefully I can give you guys some information in one field of engineering that will help you make that decision. Another question is, what does it take to be an engineer? And not just what does it take to be qualified, but what does it take to have a happy and fulfilling career and be happy with your career choice? And there's three things that come to mind for me. One is a desire to learn, a desire to be challenged, a desire to push yourself and to be pushed by others. So it really boils down to wanting to be a lifelong learner, because you're going to be steep on the learning curve no matter how long you stay in engineering. And another thing is to like to solve problems. Because what engineers do is apply the principles of math and science and physics to solve problems. And another one is a desire to become an expert at new things. And a lot of times it's things you know nothing about, but you need to become an expert in it to do your job. So I'm a structural engineer. I work mostly on buildings, special types of buildings that are related to sports and entertainment. I've got some knowledge, but pretty limited about electrical engineering, mechanical engineering, aerospace, and other branches of engineering. So I won't try to talk about those. And you guys, I think we'll get some good exposure to that later today at the Expo. But I do have a lot of experience in structural engineering, and I've been very fortunate to work on lots and lots of very interesting projects. So I thought it would be best to tell you about the stuff that I'm involved in and the company that I work for. I'll show you a number of projects, some of which you'll probably recognize, and the things that structural engineers do, like me, on projects like these. So you guys are here today because you have an interest in engineering, and I applaud you for that. At least some of you, and hopefully all of you, are considering engineering as a major and a career. And I think today I can tell you about how I chose engineering as a major and a career. I was in your position at one time, and I've also had a son who's chosen engineering, so I've been through this decision process before firsthand a few times. In middle school and high school, for me, I was not a great overall student. Most of my interests were in sports and just doing fun things. But I did pretty well in math and science, and I had some teachers that were inspirational and encouraging to me, and asked me to consider, or encouraged me to consider engineering. And I really had no idea what engineering was or what engineers did for many years after I got that advice. So you guys have an advantage. You're here today. That's a good step. The Engineering Expo at KU here is a great way to get an idea of the kind of things engineers work on and the kind of problems engineers are solving every day. So back when I was a kid, my goal was to be a professional athlete. I didn't dream of being an engineer. But my pro athlete career, like most people, didn't happen. But the good news was I've managed to blend my love of sports into my engineering career, and I'll tell you more about that later. So I decided to major in engineering, and after a couple years in school, I decided civil engineering was for me because I had an interest in construction and building things, and especially very large things. That was just a big interest to me. So after graduating from KU, I got a job as a bridge and civil engineer and worked for a firm in Kansas City for about 9 years. And then in Kansas City, I got an opportunity to work on sports-related facilities and kind of change careers. And just a little background on the sports design story in Kansas City is it started with the design of the Truman Sports Complex, which was a separate baseball and football stadium that still exists today. And at the time, it was far in advance, much more advanced state-of-the-art facility than anything that had been built in the country so far, because it was dedicated for baseball and football, whereas most of the stadiums in that era were built as sort of round cookie cutters that did both. So sight lines, seating bowls, everything was customized, and that sort of started the ball rolling in Kansas City for sports facility design. A number of firms developed and spun off. And now in Kansas City, it's really a mecca for sports facility design, which is great if you're here. Many of the facilities around the country, almost most of them I would say, and many around the world that are stadiums and arenas and entertainment-related facilities are designed right here in Kansas City. So I got an opportunity to work with Ellerby Beckett, which was one of the big sports architects in the country. We had an in-house engineering group. And after 15 years of designing arenas and stadiums with them, Thornton Tomasseti, the company I work for now, came to Kansas City to be a part of that sports design market. And I've worked continue to work on sports projects with them and some other really interesting stuff that I'll show you more about. I'll tell you a little bit about our company. We are about an 800-person firm that specializes in structural engineering, but we do many other things. We're headquartered in New York. We've got about a dozen offices across the U.S. and about a dozen outside of the U.S. So here's our offices. So it's neat to have that global reach, to be able to be involved in projects not only clear across the country but across the world. And I think engineering of all disciplines gives you that opportunity to see the world, and it's been amazing to be able to do that. Our company is broken into what we call practice sectors. Building structure is the biggest one. That's design of new buildings, but there's other components. I think I skipped ahead, but of that, things that I've been involved with, the biggest other field is forensics, and that's the study of things after they've happened. So if a building has a problem, whether it's a collapse or related to earthquake damage or tornado damage or wind damage, people want to find out what happened so that we can make things better the next time through. Okay, so one of the things Thornton Tomasseti does that I've not personally worked on, but our company does, and we're a part of it, is design what are called super tall buildings. The one on the left is under design right now. It's actually under construction. It's called the Kingdom Tower in Saudi Arabia. It's going to be the tallest building in the world of over 1,000 meters. And just to give you a context of a building you're probably familiar with, the Empire State Building is about as tall as that 450-meter building that's second from the right. So, engineering is advancing in a lot of ways. This is one way it's advancing in building design. Most of the things that I work on are buildings not going up but going across. So long span projects are prevalent in spaces like this, because we don't want columns in the middle. We want to span across, so sight lines and everything and are not in the way. So here's some of the projects that I've worked on over the years, arenas and stadiums. I've been doing this kind of work for over 20 years, so when you're around that long, you have a lot of projects you get to work on. Here's a few of the projects. One was it's always great to work on a hometown project. Kauffman Stadium had a major renovation that opened about 3 years ago. This is a renovation project at Lambeau Field in Green Bay, where the Packers play. So being a huge football fan, that kind of stuff is quite inspirational to work on projects like that. CONSOL Energy Center is an arena. You know, the pieces and parts of the building that structural engineers work on are kind of shown in that diagram in the upper right. That's a model of the roof structure. So, you know, the architect envisions a building, sort of takes a lead actually on a building project and designing what it looks like, where the floors are, what the seating bowl looks like, and then the structural engineer has to figure out how to hold it up, you know, how to design it for all the pedestrian loads, the wind, the earthquake, everything that's associated with loading on the building. We've got to design and provide that framing to hold the whole building up. Project that just opened about a year and a half ago in New York, an arena called the Barclays Center. And something you'll notice about some of these projects is they're not normal looking buildings anymore. More and more there's extraordinary designs out there. You know, buildings aren't rectangular, they're curved, they have very unique shapes. Part of that is driven by the tools that are now available to design with. Computer-aided design methods now, there's programs that have names like Grasshopper and Rhino and SketchUp that you can take and create amazing shapes with, and those tools themselves lend to creativity and the ability of the design team to create unique structures. And it seems like, you know, one designer wants to outdo the next, so we never work on a project that's just like the last one. There's always something different, you know, by design. I talked about working overseas. This is actually a soccer stadium in Iraq that gave us a unique opportunity to learn how things are done, you know, in a part of the world that maybe we wouldn't dream of going to. So the design was very unique, a very unique facade system, and we got to learn a lot about how things are constructed in other parts of the world that are very different culturally, and you know, the workforce, what they're capable of technologically. We have to figure those things out when you're working in a foreign country. Okay, this was a project that some of you guys might have had an opportunity to go to. It's a soccer stadium in Kansas City, Sporting Park. Again, kind of a very European look. This is a new, very cool project, a new stadium for the Minnesota Vikings. And you've probably never seen a football stadium that looked like that. That's because one doesn't exist like that. Those windows there, that big glass wall on the right is actually operable doors that will rotate open. And then one entire side of the roof is a translucent material, film material called ETFE. So it's going to be a very unique facility. You know, very challenging to design the structure on that. As you can see, some of the roof structure and the wall, the structure holding up the wall in the background. And here's another good example of very unique looking sports facility. And if you guys have been watching the Olympics in Sochi, I think you can see some of the facilities that are very cool looking also. So architecture, design, look, and feel of these facilities is something, you know, the architect and the engineers want people to go and be inspired by, you know, those designs. And those create tremendous challenges. This was a project we got to work on in Tulsa, Oklahoma, that was designed by a famous architect, Caesar Pelli. This was more ordinary. This is where the Super Bowl was held this year in New York, in MetLife Stadium in New York. So it's fun to turn TV on and to see a building that you've worked on. It's, you know, and it's fun to tell people about it. This project was probably my favorite all-time project. This is a final shot. It was, again, having to learn the culture of people in a different part of the world and how construction is accomplished, and also a great learning opportunity and a great travel opportunity. And, you know, even though we didn't speak the same language with engineers over there, we communicated through engineering And so it was a really fantastic experience and an extraordinary looking building. So there's a shot during construction, and you can see all this stuff back here that looks like some kind of weave is scaffolding built out of bamboo, which is something that's not done in the United States, but almost, as much of an engineering feat as the building itself. The roof structure was being built off of the scaffolding, so the scaffolding was so that about 400 welders could be up in the air doing welding on site at one time, which is totally the opposite of what would happen in the United States. We do very little welding in the field. We do that in the shop, and when we take pieces out in the field, because labor is so expensive, we design those connections as bolted so they can go together very quickly. But in China, it's just the opposite. Labor is very inexpensive. Material is relatively highly expensive, so they can afford to do things differently, almost entirely differently than we would do in the U.S. So that's just a shot. These things that look like bugs caught in a net, those are people erecting the scaffolding, and just give you a sense of scale for how tall that was. Another area of engineering that's I've got an opportunity to be involved in at Thornton Tomasseti is called forensic engineering, which, as I said, is a study of things after they've happened, and usually after bad things have happened. So it could be emergency response if there's a sudden collapse at a place. We were involved in the 9/11 event, where not only was there two major building collapses, there was adjacent structures that were partially damaged and in danger of collapsing. So we had people on site there for 24 hours a day for about 6 months, trying to help ensure that there wasn't other safety issues and people getting hurt while they were doing the work around the site. This is an example of a forensic project. It's the Superdome in New Orleans that was hit in 2005 with Hurricane Katrina. There was some pretty major damage there. It was used as a shelter during the event, but the roof blew off of it, and there was quite a bit of damage. So we worked on a major renovation project of that building after Katrina. And this project right here, it was about 3 years ago. There was a tragic occurrence of a collapse of a temporary stage structure in Indianapolis at a state fair. And it was a concert event, and some of you might have seen structures like this at outdoor concerts, where there's a temporary stage structure and an overhead structure built to house the band. And lots of things are hung from the overhead, the speakers and the lights, but these things, in a lot of cases, aren't fully designed by an engineer, even though there's lots of people around them. They've kind of, this is a case where what happens if there's not proper engineering, and they were just really constructing these things based on what they've done before and rules of thumbs, and saying, well, I've put this together like this 100 times and never had a problem, so what's the big deal? Why do I need an engineer? Well, this is why. A sudden wind came up, the structure failed laterally, and we were called in to investigate the cause of the collapse by the state. The state wanted to know, what happened, what should we do next time, and what can other people learn from that. And so, the big question is how do we approach a forensic engineering process? How do we figure out what went wrong? What are the important pieces of information to gather? So there's a whole methodology that I've been learning since I've been at Thornton Tomasseti from other experienced forensic engineers on how to approach something when you pull up to a building or a structure and it's collapsed. Okay, now what do we do? We try to gather as much information as possible. So there was a survey There was on-site testing, there was wind tunnel testing, we did metallurgical evaluation and physical testing of components. We modeled this on a computer, and we did structural analysis and calculation. So the first part of it was just kind of, there were no drawings that labeled every piece and part on the of this entire structure, so we had to do that ourselves. So we created serial numbers for all the components, of which there were thousands. There's a way to do a laser scan survey now where lasers and reflectors can be set up around the perimeter of a structure, and it creates a point cloud that you can import into a computer program to give you a graphic image of everything that exists out there. FEM is finite element modeling, and that's a special kind of the most accurate type of structural analysis that can be done. So based on site measurements and data that was available for the different components, we sort of reverse engineered the structure, as to what happened. And we also then were asked to go back and say, well, what should have been done? What, if an engineer was called in, would he have been able to prevent that collapse? Those are the kind of questions that are asked. So that's a full-scale model of the stage structure with all the main components hanging that's inside of a wind tunnel. Because this wasn't just an ordinary building, and looking, just the wind pressures up in a building code or any other book is not going to tell you, may not necessarily be realistic about the wind forces on a structure like that. Here's some photos of some material testing, breaking welds, finding out, what is the real strength of that weld? Does it match what it was supposed to if we calculated it? Evaluating cracks and doing material testing, identifying all the components. And I think this next set of slides kind of shows the analysis. The structure was a bunch of aluminum towers that was really not stable laterally by itself, so it had to be guyed down to braces. And so what they did was these JBs are chunks of concrete. They're Jersey barriers. You see them along the side of the road sometimes. So what they had done is guy the tops of these towers back to these Jersey barriers, and the wind came in from this direction. In this next set of slides, okay, so here's kind of some diagrams of of what came out of the wind analysis from the wind tunnel study. They were able to tell us on each piece and part of this structure, the roof and the individual tower members, what those loads were. Now we're to the slides that show kind of the failure sequence. And you can see the method of this thing being held down was this chunk of concrete out here that weighed about 3,000 pounds, but there was also some braces down here. And this component right here, we figured out, was moving first and starting to fail. So there was a sequence. When this started moving, this one then started to slide. And then this one had essentially failed. And then the next one was, this one that was starting to slide and then fail. And eventually, those tower components are fine as long as they're perfectly straight. But you get to a point where they're leaning so far and they lose their ability to carry vertical load. So at some point there, we're to the point of no return, and we can calculate that. There's another a stadium actually that was damaged, the Houston Texans Stadium in Houston, Texas, that was damaged by a hurricane that we worked on. Another service that we offer is related to construction. And contractors need engineering help also, say for erection, designing things before they're completed, because most engineers typically will design a building and model it in a computer where it's complete, not where it's half built. So that part of where it's built in stages, the whole thing has got to be stable, because there could be wind loads, earthquake loads, all other kind of loads during construction that have to be evaluated. On some of those slides, you saw some very elaborate buildings facades. So that's, we've got people that work in our company that specialize in just the design of special building facades. On projects like this, a stadium in Russia that's actually an arena on the right side and a stadium on the left side that's combined into the same building. Another really fun area that I've gotten an opportunity to be involved with is related to the arena business and rigging. It's concert and event rigging. And we have a number of venues where we've designed the building and the roof structure and know the loads that are designed for. They may have been designed 10 or 15 years ago. Now shows are getting bigger and heavier and sometimes exceed the stated load limit. So we get hired to come in and evaluate the temporary loads that are going to be hung from those roof structures. This is the Country Music Awards show, and you can see there's really nothing on the ground except for the stage. Everything else is hung from the roof structure above, and for this show there was something like 700 points that had to be hung from the roof structure. So they need to have that question answered. Okay, can my roof hold that? Or what happens if it snows and I have this concert? And in this case, we do have a snow restriction for this event, and had to limit it. And if there happened to be a big snow over, say, 6 inches or something like that during the event, we'd have to start lowering things to the ground. Building sustainability is another thing we get involved with. You know, energy usage is not just with automobiles. There's a huge percentage of the energy burned in the world that's used by buildings. And so a big emphasis now on new building construction, and when old buildings are being renovated, is how can we make those buildings more energy efficient and more usable and friendly to people in a lot of ways. So back to why be an engineer. The world needs engineers. Technology is advancing at such an exponential rate. It's amazing. And engineers are the people that can drive the future. And engineers are major contributors to society and helping shape the future of the world. Another reason is because there's lots of good paying jobs. I know a lot of engineers, and I don't know any unemployed engineers. There's lots of demand. The demand is growing, and if you do some research, starting salaries and salaries throughout your career are really good, competitive, and it's just a very solid. You know, if you get an engineering degree, you're going to have a job when you graduate. And it's also a very rewarding career. There's many areas of engineering, many roles that engineers play in companies and in projects in society that are interesting and challenging. And you know, the lifelong learning is really a big thing. Getting bored, I found, is the absolute worst thing with working. I'm almost never bored. Time goes very quickly. I'm always excited to come to work. And you never stop growing as a person. So my advice for you guys is to be good students. Work hard in school. Get the most out of it. You know, do your best to learn and get good grades. Learn more about engineering. Today's a great first step, but there's lots of other great resources. Discovery Channel's got a great project program that always interests me. It's called Build It Bigger, and I love big things. And you know, there's some great programs on TV. Company websites are getting better and better all the time. We've got a great website, thorntontomasseti.com, that you can go to and learn more about us. And talk to engineers that you know, and visit companies. that's really a great way. There's so much to know that you're not going to learn in middle school and high school about what engineers truly do. You need to go out. Today's a great first step, but also do everything else you can. And enjoy your day today. Learn as much as you can and ask lots of questions. And thank you very much. It's been a pleasure talking to you guys.